Hello, today we're continuing with our series on quantum mechanics concepts, today looking at the harmonic oscillator. Classically, you can think of a harmonic oscillator as a spring. Here is a spring which is suspended from the ceiling, and in its ordinary state with no load on it, it may reach to this point here. Then we put a load on it, and of course the spring stretches. So we put a mass on it, mass m, and it stretches to this point here, so that the extension of the spring is a distance x. And we say that the force on the spring is equal to the spring constant k times the extension x. And the force, of course, is just the mass times the gravitational attraction, so that's mg is equal to kx. And that's essentially a means by which you can weigh things. It's called a spring balance. Now, if I were to take this mass and pull it down a little bit and let go, then of course the spring is going to oscillate up and down about a mean position. And that oscillation will be a sine, or if you like it, a cosine term. So you get essentially the oscillation according to a sine or cosine wave pattern. And the frequency of that pattern, omega, is given by the square root of k over m, where k is the spring constant and m is the mass that is on the spring. And from that you can see that k is equal to omega squared m. From this formula you just square both sides, you get omega squared is k over m, so k is omega squared m. Now it is the fact that so much in nature has this kind of sinusoidal description. Even electromagnetic radiation, as we saw in our series on EMR, has a sine or cosine wave. So in the classical days, before quantum mechanics ever came on the scene, you can see why scientists were attracted to the idea that at the atomic or molecular level, there was something that resembled this kind of oscillation, this spring oscillation, this harmonic oscillation, because this is actually called simple harmonic motion when it oscillates, and I've done a video on that. You can see how they would assume that there must be something at atomic or molecular level which is oscillating so as to produce these sine and cosine waves. So the idea of a harmonic oscillator being the essence of what's going on at the atomic and molecular level was around in classical days. So now let's see if we can also apply it in quantum mechanics. Now we know that energy is kinetic energy plus potential energy. That's classically how we think of it. And in classical terms, that's a half mv squared. And when we think about the spring, the potential energy of a spring is a half kx squared, where k is the spring constant and x is the extension away from the, as it were, the normal position, or the when you've got the spring oscillating up and down about the normal, then x is the extension away from the mean position. We can write a half mv squared, as we've seen before, as simply p squared over 2m, where p is the momentum. And of course I can write kx squared as omega squared m x squared, because k is omega squared m, as we showed just a few moments ago. Now I'm going to set m equal to 1. M equals 1, just to get that out of the problem and make life a little bit easier. So now I've got that p squared over 2 equals, p squared over 2 plus a half omega squared x squared is energy when m equals 1. But of course I can now write this as the Hamiltonian, because the Hamiltonian is energy. The only difference is that the p and the x now become operators. So I've got p operator squared over 2, and here I've got half omega squared x operator squared. But remember that x operator squared, that is the whole point about the operator acting on psi, simply gives you the position psi. That's the whole point. So the operator will give you the position. So we can replace the operator just by the position. Now we've got to look and see what this is going to amount to. Well, this of course is going to be minus I h bar d by dx all squared. That's p, the operator p we showed was minus I h bar d by dx all squared. Now I'm going to do a physicist's trick at this point, and I'm simply going to make h bar equal 1. I'm simply going to take it out because it clutters up the equations, and then when we get to the end it will be very obvious where it goes back, and I'll show you when we get there. So to save us worrying about h bar squareds all over the place, let's just think about this. Minus I times d by dx squared. Well, minus I all squared is going to give you minus 1, so that's going to be minus. And d by dx squared is of course d2 by dx squared. So I can replace p squared over 2 by saying that that is a half. Oh, and indeed it's a minus a half d2 by dx squared. And then plus a half omega squared x squared. So if I now allow h to act on psi, then h is this. So this is going to be minus a half d2 psi by dx squared, and I should put psi of course in the Dirac notation, plus a half omega squared x squared psi. And that of course is going to equal the eigenvalue E times psi, because h psi, the Hamiltonian acting on psi, gives the eigenvalue E acting on psi. So we need a solution for psi. And as one always does in these circumstances, we say let's try this solution, that psi is equal to the e to the minus omega x squared over 2. And when I say let's try that, of course I know where I'm going, so I know that by happy coincidence that is going to prove to be a good guess. But now let's work it through. What is d psi by dx? Well, you bring down the minus omega over 2. That's the first thing you have to do. Then you have to differentiate the x squared. That gives you a 2x. And then you're left with e to the minus omega x squared over 2, the original term. That's the first differential. Now we need to do it again. d2 psi by dx squared is going to be, well, again, you bring down another minus, well, sorry, this is now the differential of a product, 2x and this term here. So it's going to be minus omega over 2, which is that term here. And now we first do the differentiation with respect to this term, but leave that one alone. So we are simply going to get 2. And then this term is just, of course, psi. And then you add to that this term, which is minus omega over 2. So it's minus omega over 2. This term stays the same now, 2x. But now we have to differentiate this. So we're going to get another minus omega over 2. And then from here we're going to get a 2x. And then we're going to just be left with the e term itself, this term itself, which of course is psi. Which at first sight looks horrendous, but let's just check. This 2 will cancel this 2. So we've just got minus omega psi. This 2 will cancel this 2. This 2 will cancel this 2. And we've got a minus omega times a minus omega gives you plus omega squared. And an x times an x gives you plus x squared. So we're going to get, from here we're just going to get minus omega psi. And from here we're going to get plus omega squared x squared psi. So now we need to plug this term, which is d2 psi by dx squared, in the Hamiltonian that we derived a moment ago. So the Hamiltonian, you may remember, was minus a half times d2 psi by dx squared. Well, we've just worked out what that was. It was minus omega psi plus omega squared x squared psi. So that was our d2 psi by dx squared. And then we had to add to that plus a half, and this is the potential energy term, the kx squared term, which we had shown is equivalent to omega squared x squared psi. So look what we've got. We've got minus a half omega squared x squared psi plus a half omega squared x squared psi. That's 0. That term and that term disappear. And what you're left with is that h is equal to minus a half times minus omega is just omega over 2 acting on psi, and that equals, of course, E psi, because, sorry, h should be acting on psi in each case here. So h acting on psi is omega over 2 psi, which is E psi, and that means that E is omega over 2. And now you can easily see where the h bar goes. When we put it back in again, it's obviously going to go there because E is energy, omega is a frequency. In order to multiply a frequency into an energy, remember this term, E equals hf, you multiply h by the frequency, or you multiply h bar by the angular frequency in order to get an actual energy term, so that dimensionally they are consistent. So we can just obviously put back the h bar term, and we find that the energy is h bar omega over 2. So what have we done? We've essentially taken the Schrödinger equation, which says that you take the energy, which is the kinetic energy plus this is the kinetic energy term plus the potential energy term. We've worked out what that kinetic energy term is for the harmonic oscillator, and this is the potential energy term for the harmonic oscillator. We've said that h psi equals E psi, but h psi from this simply comes out to omega over 2, from which we've worked out that E is omega over 2, which is strictly h bar omega over 2. So we've essentially established a ground state energy of h bar omega over 2 for our harmonic oscillator. Now you'll recall that we said that h, which is essentially energy, can be regarded as p squared over 2m plus a half omega squared x squared. And actually, I should take the m out because we had set the m to equal 1. So h, we said, was p squared over 2 plus half omega squared x squared. P is the operator. X, it can be the operator, but then x operator simply returns the value of x, so we can put the number x in here. So I can just obviously write that as 1/2 into p hat squared plus omega squared x squared. And I want to factorize that and see where we go. So that's going to be 1/2 into p plus I omega x, p minus I omega x. If you look at that, classically, p times p gives you p squared, plus I omega x times minus I omega x gives you minus I squared, which of course is plus 1, times omega squared x squared. And classically, this times this and that times that cancel out. And so that's a perfectly valid classical factorization of this term here, where of course these remain the momentum operators. But if I now become quantum mechanical, and I start at this point here, and I say, well, now let's just multiply that out. Fine, p times p will give me p squared. And plus I omega x times minus I omega x will give me plus omega squared x squared for the reasons I've just given. But now we have to say that we've got plus I omega. And now what have we got? We've got I omega xp minus I omega px. And classically, of course, that would equal 0 and that term would go. Haha, but we're not talking classically anymore, we're talking quantum mechanically. And we've met this before. The operator x and the operator p do not commute. That is the commutator of x and p. And it equals IH bar. It does not equal 0. Now remember, in the language we're talking, we're dropping the H bar because we can just stick that back in at the end. So this is essentially, for our purposes, just equal to I. And so this term here is equal to I. And if you multiply I by I omega, you get plus I squared omega. And that is equal to minus omega. So take all that lot out and put minus omega. So now we've found that h is a half p squared plus omega x squared minus this quantum mechanical factor here. But we know that h is actually this term here. So what we're going to say is that if you want to express h in this form here, a half p plus I omega x into p minus I omega x, then in order to make that equivalent to this, you have to add an I omega over 2, which is essentially the minus half I omega here. If you want to correct this, you will need to add an I omega over 2 in order to get back to the original. Consequently, if you're going to adopt this route, you have to add an omega over 2 at the end in order that this will be equivalent to this. So now I want to ask myself, what is the commutator of the term p plus I omega x with the other one, p minus I omega x? And the reason I want to do that, actually I need a bracket there as well, the reason I need to do that will become apparent in a few moments. But let's just do the commutator first. We don't actually need to write it out in full because we know that it's going to be this times this minus this times this. And you'll see that most terms will just fall, because you're going to get a p squared minus a p squared, so that goes. You're going to get this squared minus this squared again, and that will go. And the only thing that's going to be left is going to be the cross terms, from which you're going to get, remember you've got to multiply this by this, so it's going to be I omega xp minus px. That is going to be from this term multiplied by this term, and then you will have to subtract this term multiplied by that term. Well, that will be I omega into this term minus this term will be px minus xp. So that will be the consequence of doing the commutator here. And you'll notice that we've got an xp minus px, which is the commutator of x with p. And here we've got a px minus xp, which is the commutator of p with x. But I said you could convert this to this simply with a minus sign. So I can effectively make that xp minus px simply by changing the sign here. And now you see I've just got, let's get rid of those, now I've just got two lots of this, so that's 2I omega into xp minus px, which is 2I omega times the commutator of x with p. But we know what the commutator with x with p is, it's IH bar. And since we're dropping the h bar in this process, we've now got that it's 2I squared omega, which is of course I squared is minus 1, that's minus 2 omega. And you'll see why I want to do that in just a moment, because I'm going to create two things. an A plus, which is going to be my P plus I omega x term, but I'm going to divide it by the square root of 2 omega. And I'm also going to create an A minus, which is my P minus I omega x term, also divided by the square root of 2 omega. And the reason I've done that is because now A plus, A minus, the commutator of A plus with A minus, is now going to be equal to minus 1. Remember, the commutator of P plus I omega x and P minus I omega x came out to minus 2 omega. Consequently, if we divide these two sides by the square root of 2 omega, that will cancel the 2 omega that you get here, and instead of minus 2 omega, you'll get minus 2 omega divided by 2 omega, and that's minus 1. Well, you'll see that P plus I omega x is equal to the square root of 2 omega times A plus, and P minus I omega x is going to equal the square root of 2 omega A minus, because we defined A plus to be this term divided by the square root of 2 omega, and we defined A minus to be this term divided by the square root of 2 omega. So consequently, if H is going to be 1/2 of, and then you remember we had P plus I omega x times minus P minus I omega x, and then we had to add a plus omega over 2 at the end. Well, this term can now be written as the square root of 2 omega A plus, and this term can now be written as the square root of 2 omega A minus. All right. Originally, the Hamiltonian had P plus I omega x times P minus I omega x in these brackets, plus the correcting term omega over 2, which we showed why we needed that. All I'm doing is to substitute for these two terms inside the brackets. So that is now my new form of the Hamiltonian. That's just going to give me that the Hamiltonian is going to be equal to omega into A plus A minus plus omega over 2. So now let's see what the effect of taking A minus and acting it on the wave function psi is. Remember that we said we would try, because it turned out to be right, we would try for our value of psi e to the minus omega x over 2. Sorry, omega x squared over 2. Well, A minus, you may remember, was 1 over the square root of 2 omega times P minus I omega x. That is, in fact, how we defined A minus. And we're going to act on psi. But psi is e to the minus omega x squared over 2. But P, of course, is minus I h bar d by dx. We've shown that. And in our terms, since we're dropping the h bar, what we're effectively saying is that P is minus I d by dx. And so now we can draw the minus i's on the outside. So we now get minus I over the square root of 2 omega by taking this minus I and this minus I out. And we've now got d by dx plus omega x times e to the minus omega x squared over 2. And that's going to be equal to minus I over the square root of 2 omega. That's this term here. First we'll do the differentiation. D by dx of this term here firstly brings down the minus omega over 2. Then it brings down the 2x. And then it just leaves this term, which of course is psi, plus omega x times psi. But look at this, the 2's cancel, and I've got minus omega x psi plus omega x psi. Well, that's 0. Nothing. So the effect of A minus on psi is to give us nothing. This is an annihilation operator. It acts on the wave. Remember, I told you what the wave function is, but when it acted on that wave function, it gave us absolutely nothing. It has destroyed the wave function. Well, what about A+? What did that do to our wave function? Well, clearly that is actually going to produce some kind of new state. I don't think it's going to produce nothing. That's what A- did. So let's consider this beast here, the Hamiltonian acting on that new state, that should be A+, which of course is an operator, but A+ times psi. Well, that is going to be equal to the H acting on any eigenvector is going to give you an eigenvalue. So that's just going to be equal to lambda, which is the eigenvalue driven out by H. A plus psi. But that eigenvalue, of course, when H is the Hamiltonian, that eigenvalue will be the energy. So we've got the energy times this state, which is the combination of A plus and psi. Now we showed what H was. It was omega, A plus, A minus, there's a bracket A plus, A minus, plus a half. That is simply H. And that acts on this state here, A plus psi. And it gives us E, A plus psi. So let's just work this through and see what we get. We get omega A plus A minus acting on A plus of psi plus omega times a half, which is omega over 2, acting on A plus of psi equals E, A plus of psi. Now I just want to look at this term here, and I want to recall that the commutator A plus A minus equals -1. It was something we showed a little earlier. And if that is true, what that actually means, if you write it out in full, is that A plus A minus minus A minus A plus equals -1. That is the definition of commutator. And that means that A minus A plus is equal to A plus A minus plus 1. Right, if you take that onto the other side, it becomes a plus. If you take the 1 on the other side, it becomes a plus. So plus A minus A plus is equal to A plus A minus plus 1. So what I want to do is to substitute the A minus A plus here for A plus A minus plus 1. So let's just remember that. That was omega A plus, and now for A minus A plus I'm going to put instead A plus A minus plus 1 acting on psi, plus all these other terms which remain the same. So I'm not going to write those out yet, because I'm going to point out what happens here. Look at this great term here. The rule is you always act on the one that's nearest to the eigenvector. So the first operator that's going to act is A minus. What does A minus do when it acts on psi? It annihilates it. It creates 0, nothing. And once you've created nothing, all of this lot don't matter anymore. You've now got nothing. You can't do anything with it. So this lot acting on psi produced nothing. So the only thing you've got left is omega A plus times 1 acting on psi plus omega over 2 A plus acting on psi is equal to E A plus acting on psi. So in each case we've got an A plus psi, A plus psi, A plus psi. So what have we got? We've got omega plus omega over 2, which is of course 3 over 2 omega, is equal to E. Now you'll remember that the ground state that we started with was that E was omega over 2. That was several minutes ago we derived that. So by acting with A plus on psi, we have effectively increased the energy by omega. And of course we now know that what you've got to do is to put an H bar in here, because that's the way to convert frequency to energy. So since we started with a half h bar omega, and we've now got 3 over 2 h bar omega, what that actually means is that we have increased the energy by h bar omega, from a half to 3 halves h bar omega. So what A plus does is it increases the energy by a quantized amount of h bar omega. And having got to the new state, if we acted again with A plus, we would get to 5 over 2 h bar omega. And if we acted with A plus again, we get to 7 over 2 h bar omega. A plus just keeps pushing the energies up by a quantized amount of h bar omega. And my plan is that I now hope to use the quantum mechanics concepts, which I appreciate have just been conceptual because I've designed it that way just to get the concepts across, in a new series which will be on particle physics, which will show how these operators actually make particles, create higher energy particles, and so on.